Everyone is completely wrong about the AI supply chain right now. They think TSMC can't print enough chips. But chips aren't the problem anymore. The real bottleneck is something else entirely, and it is much worse. For years, the AI cycle has centered on a single industrial node, the race to print macroscopic circuits on silicon wafers. The assumption is that raw chip fabrication is the absolute speed limit for large-scale computing. Between 2020 and 2023, the physical limit for any AI model was the number of logic dies coming off the line. This constraint has been largely cleared by massive capital investments. This area map breaks down current global logic die production. The 4 largest AI designers in the world, NVIDIA, Google, AMD, and Amazon, collectively consume 12% of the total supply. Foundries have widened the silicon pipe to meet the remaining demand. By the end of 2026, TSMC plans to push 3-nanometer production to 180,000 wafers per month. Scaling AI now requires moving through a rigid sequence of 6 physical stages. It starts with computing demand, which triggers the fabrication of logic chips. Then comes advanced packaging, the addition of high-bandwidth memory, building the data centers, and finally, supplying megawatt power. The scarcity has effectively migrated away from the transistor and toward macroscopic infrastructure. The first new physical wall is advanced packaging. AI processors have reached the maximum size limit for a single monolithic piece of silicon. To bypass this limit, manufacturers use a technology called CoWoS. This process physically stitches multiple separate logic and memory components together onto a single base layer. This capacity gauge shows the resulting structural supply squeeze. AI chips currently consume over 90% of global advanced packaging capacity, resulting in wait times as long as 52 weeks. The second major physical wall is high-bandwidth memory, the specialized storage required to feed information into AI processors. HBM is incredibly raw material intensive. Each memory stack consumes 3 times the silicon volume of standard computer memory, reducing total units a factory can output. This structural memory cap means production will fulfill only 60% of global market demand through 2027. Physical infrastructure is the final and the most rigid physical wall. The processors inside these facilities draw massive amounts of electricity. Modern AI data centers are entering the gigawatt era, with single campuses requiring the same power as a mid-sized city. Deploying these clusters depends on heavy, specialized hardware, like high-voltage transformers. These units weigh hundreds of tons and are manufactured on multi-year cycles. Even when the hardware is secured, plugging these facilities into the national power grid requires engineering studies that take years to finish. This data visualization compares incoming power requests against available supply. The current U.S. interconnection queue now mathematically exceeds the total existing capacity of the entire grid. In the artificial intelligence industry, it is a fundamental rule that any complex system is limited by its slowest growing physical bottleneck. This timeline compares lead times across the chain. Silicon fabrication takes 16 weeks. Advanced packaging extends that to 52 weeks. Plot a match. Acquiring high-voltage transformers takes 5 years, and expanding the grid takes 8. The growth rates are moving in opposite directions. The power grid is expanding at 15%, while AI energy demand is exploding at 165%. Trillions of dollars in AI capital investment currently risk generating completely stranded, unpowered silicon. Winning the global AI race through the end of the decade depends on the speed of pouring concrete and pulling copper.